Hey guys, welcome to the live stream for this week. We're doing it on a Monday this week because of some stuff I got going on Tuesday and Wednesday. So I thought this might be a good day because we did an all-day science day today in class. We learned about, minerals. We had all those different stations. So today we're going to talk about some math this evening. So if you feel like you're struggling on fractions or decimals or anything that we've been talking about in class, please ask questions. Let me know some things that you don't feel that comfortable with on homework, and we'll go over those things. As always, I will I will watch Google Classroom as well as YouTube comments. So make sure that you're commenting on either one of those places. So we're going to go ahead and get started on math homework for tonight. So to stop at the top of math homework, we notice we see an addition, a subtraction, a multiplication, and a division operation problem using decimals. So the one thing I want to start out by doing is I want to start out just by reviewing our decimal place value because that's important. Now, remember that if we're looking at this first problem, you see 19 plus 2 and 493 thousandths. Now, we want to pay close attention on what number is in the tens place, what number is in the ones place, and then our tenths, our hundredths, and our thousandths. Now, keep in mind that our largest decimal place value is our tenths, our next largest is our hundredths, and our next largest is our thousandths. Think of something that's split up into 1,000 little tiny pieces. That would make those pieces really small. So you see 2 and 493 thousandths. The 2 is our whole number there. So that means it's 2 wholes. In the number 19, the 9 is in the ones place and the 1 is in the tens place. So what we're going to do is we're going to line up the numbers in the ones place and with the numbers in the ones place in the other problem. So notice it's going to look something like this. So 19 plus 2 and 493 thousandths. And because I don't have a decimal in that first number, all I have to do is add 0.000. Now, a lot of people will say, well, wait a second, you've changed that number. But if we put a decimal here, that number is still 19. So keep that in mind. We haven't changed that number at all because it says 19 and nothing. 19 and nothing more is still 19 wholes. So if I add those two numbers together, this is one that you could probably do mentally that you may not have even realized. We get 21 and 493 thousandths. All right, moving on to the next one. 144 minus 15 and 344 thousandths. Now, a lot of people still get in the habit of putting that 144 as the second number, and the reason we often do that is because it has less digits. A lot of people will say, well, it looks smaller, but think about it before you start. Which one of those two numbers is the larger number? We have 144 wholes, or we have 15 wholes and just a little bit more. Not even 15 and a half, because remember 500 thousandths would be half. So it's not even 15 and a half. So I'm thinking of subtracting a really big number minus not nearly as big. So what I'm going to do is I'm going to take 144, and again I'm going to line up my place value. I'm going to ask myself what number is in the tens place, what number is in the ones place, and then the tenths, the hundreds, and the thousands. So what I'm going to do is I'm going to put the 15. It's going to look something like this. Because what I'm doing is taking 144 wholes minus 15 wholes, but then I still have to subtract the 343 thousandths. So what I'm going to do up here at the top is I'm going to put a 0.000. Very similar to what we did on that last problem. So I'm going to have 144 minus 15 and 343 thousandths. I'm actually going to let you guys finish that problem now that we have it set up for you. I'm going to let you finish that. All right, moving on. We have 2 and 7 tenths times 2 and 48 hundredths. Now, one thing we're forgetting, and one thing that we did a lot in class, keep in mind, a really quick way to multiply decimals is by getting rid of that decimal completely. So one way we do that is, remember, if I take this number 2 and 7 tenths and I move this decimal over one time, notice now we have the number 27. Well, what I'm actually doing when I move that decimal over one time is I'm taking 2 7/10 and I'm multiplying it by 10. So when I multiply it by 10, I end up with the number 27. Now the reason I like the number 27 is because that's a whole number, that's an easy number to work with. So I'm going to take the number 27, and then I'm going to take 2 48/100, and I'm going to move the decimal over here over, let's see, 2 times. Now, the reason I'm going to move it over 2 times there is because we had digits into the hundredths place. Now, if I move it over once, that's multiplying by 10. If I move it over twice, that's the same as multiplying by 10 twice, which is the same as multiplying by 100. So you're going to get 27 times 248. Now, once you multiply 27 times 248, you're going to take the answer of whatever it is that you get to that, and because we multiplied by 10 here, and we multiplied by 100 here, in the end we have to make up for that. So notice in the beginning we multiplied by 10, and then we multiplied by 10 and by 10. So in total we multiplied by 10 3 times. 10 times 10 times 10 is 1,000. So in the end we're going to need to make up for that by doing the opposite. So what we're going to do in the end is whatever we get as our answer here, we are going to divide it by 1,000. We're going to take our answer and divide it by 1,000. So I'm going to let you guys solve that problem. Now, I want to address something that I just saw in the questions. Somebody said, when would we, I'm going to read it exactly word for word. When would we need to subtract decimals in real life? Well, think about all of the word problems that we do all the time where you have a certain amount of money and then you go to the store and you buy something that is a decimal. You're going to get a change back, and that involves decimals. So subtracting decimals we do in word problems all the time, and those are real life situations when you're working with money or you're working with a weight or lots of things in real life you're going to do that. Same thing with division. We've talked about if you go to a restaurant or something and your bill is not a perfect whole number, your bill is a decimal maybe, and you're splitting it up between multiple people, that would be an example of division. So these are real things that we use a lot in real life, actually. All right, and the last one here, we'll work this one out together. 1,259 28/100 divided by 6. 1,000, I need to look at that one again. 1,259. 1,259 28/100 divided by 6. So I am going to start off by saying, well, first I'm going to think about this number. I have 1,259 28/100. So let me make my decimal a little bit bigger. In your head, you might be thinking, what type of number would make sense here? Well, I'm thinking I know my answer has to be bigger than 100, because if I gave 100 to each of these 6 groups, that would be 600. Now, I might say my answer also has to be bigger than 200, because if I gave 200 to each of these 6 groups, that would be 600 and another 600, which is 1,200. Now, I might say my answer is probably going to be close to 200, because I know my total is 1,259, which is pretty close to 1,200. So I know my answer is going to be close to 200. It's going to be just a little bit bigger. So ask yourself before you start a question what types of answers will make sense. So I'm going to say there are 2 groups of 6 and 12. Subtract and we'll get 0. We're going to bring down our 5 in our tens place. How many groups of 6 are in this 5 tens? Well, there's none, because we can't put a 10 in each group if there's only 5 of them. So I'm going to say 0, and I'm going to bring down my 9. How many groups of 6 are in 59? Well, if we count by 6s, 6, 12, 18, 24, 30, 36, 42, 48, 54, which is 6 times 9. subtract, and we will get a 5, and we're going to bring down our 2. So that's saying if we have 5, and remember that was 2/10, so 52, how many groups, that's the same as looking at it as 52 tenths. How many groups of 6 are in those 52 tenths? Well, we're going to take 6 times, we just counted our multiples, that's going to be 6 times 8 is 48. I'm running out of room here, but we have a 4. I'm going to bring down that 8. And again, we get 48, and that's 48 hundredths, keep in mind. So we're saying how many groups of 6 are in that? Again, 8. And we'll end up with our final answer there. So 209 and 88 hundredths. Jasmine, I saw you put, why can't people price things in whole numbers like $5? Well, sometimes they do, but sometimes they don't. And sometimes they price things in numbers like $2.99, because in your mind you think, oh, that's not as much as $3, even though it's only 1 cent away. So sometimes that's why they do that. All right, we're going to try to go pretty quickly through this part. Compare 3/5 and 63 hundredths, and how can you figure out which is bigger? Now, you have a lot of different options here. I'm going to give you 2 different options to start off on this one. 2 ways that I would do this. Number 1, you have a fraction and you have a decimal. One thing that I might try to do is to take that fraction like this and to turn it into a decimal. Now remember, when we're talking about decimals, we have a tenths place, we have a hundredths place, and we have a thousandths place. So one thing we would need to do is to take this denominator and either change it into a tenths pieces, hundredths pieces, or thousandths pieces. Remember, one way that we can do that, in this case we can make it into tenths, is we can multiply by the same thing on the top and the bottom. Now, the reason why you can do that and multiply by the same thing is because if you multiply, remember, by the same number on the top and the bottom, that's like multiplying by 2/2, or 2 halves, and 2 halves is the same as 1 whole. When you multiply a number by 1, you're taking one group of it, you're not changing the number at all, that is the same number. Now, if we multiply by 3/5, we will get 6/10, which means that it looks like this. Now that you have them both as decimals, much easier to compare. Now I'm going to give you a second way that you could probably make this work. A second way is you already have 3/5 as a fraction. What if you changed 63 hundredths into a fraction that looks like this? Now you have 2 fractions. Now keep in mind these 2 fractions are very different. They're not the same size pieces. So one thing we could do here is we could take these 2 numbers and we could actually make a common denominator. Now one way we could do that is we could take 5 and multiply. I'm going to do it on this side just for room. 5 times 20 is 100, and 3 times 20 is 60. You would see 60 100ths. And now you're comparing 60 hundredths to 63 hundredths. So I would either suggest making them both into decimals, making them both into fractions, and then making common denominators. And either of those ways would be great. Now let's look at the second one. The second one I might approach a little bit differently. Notice these are both fractions. I'm going to write them a little bit bigger. We have 5/6 and we have 7/8. Now, the first thing that pops out to me in my head is that both of those fractions are missing one piece from being a whole. Now, what I mean by that is that 5/6 is 5 out of 6. Think of a pizza. That means you have 5 out of the 6 pieces that you would need for a pizza. So here you are missing 1/6. And here, in order to be a whole, you're missing 1/8. Now, keep in mind that you're only missing one piece in both of these, but the piece you're missing is different. Now, 1/6 is a bigger piece than 1/8, because think of a pizza that's only split between 6 people. The pieces are going to be slightly bigger because there aren't as many people, versus a pizza that's split between 8 people. Because there are more people, the pieces are going to be smaller. Now, 7/8 is missing a smaller piece. Because it's missing a smaller piece, that makes it the larger number. So in this case, logic can actually get you pretty far just by thinking about which is missing a smaller piece, which is closer to a whole. And in this case, 7/8 is a little bit closer to a whole. A second strategy you might try here is to take 5/6 and 7/8. So we have those two numbers there. I might take those two numbers and make a common denominator. Now, remember one way that we did that was we took our 6 and we wrote down some multiples of 6. So 6, 12, 18, 24. Then we took our 8 and we wrote down some multiples of 8. 8, 16, 24, 32. Notice I named the same multiple twice. That would be your common denominator. Once you have those two numbers as a common denominator, they're very easy to compare. So that would be two ways I would do that. Now, a third way you could do it is you could change both of those numbers into a decimal. We'll talk a little bit more about that in class tomorrow. It might be a little bit more work, but that also is possible. All right, so we are going to move on to the backside. First one, well, first off, we're looking for the 7th number in each pattern below. Oh, one thing I want to move on. I saw Luke put the smaller the bigger. That's true. The smaller the denominator is split into, that means it's split into a fewer number of pieces. That means those pieces are going to be bigger pieces. That's an important piece to know. All right, so we're looking for the 7th term in each pattern below. So we have 2, 4.5, 7, 9.5. We're looking for we have 1, 2, 3, 4 terms, which means we need to find 3 more. Now, the thing I noticed right off the bat is we are first involving decimals. Now, when I go from 2 to 4.5, we're either multiplying by something or adding something. The first thing that pops out to me is it must be adding something because we're going up by a small amount each time. Our number isn't getting big fast, and that usually would mean multiplication. So I know that from 2 to 4.5, is 2.5. I've went up by 2.5. So I'm going to see if the same thing works from 4.5 to 7. So if I take 4.5 and I add 2.5, remember a half is 0.5, I will get 7. Because of that, I know that each time I'm just going to add 2.5. So to figure this out, I would take 9.5 plus 2.5. which gives me 12. I'm going to take that number and add 2.5 again, which would give me the 6th number, which is 14.5. And then I'm going to take that number, 14.5, and I'm going to add to it 2.5. And I'm going to get 17 wholes exactly. So notice sometimes we're just adding a piece. We got to look for that piece, even if it is a decimal. Now the second one, you're going to notice this was a 50. I changed it. The second one, you're going to notice that your pattern is going down from 50 to 44.5 to 39 to 33.5. Notice there your pattern is going to be subtracting. Now, in order to find what we're subtracting, my first suggestion would be to take 50 minus 44.5, looking like this over here, right here. I would take that and I would see if you can find what we're subtracting. Now, once you've found what we're subtracting each time, you're just going to do that 3 more times, and that'll give you the answer. So I'm going to let you finish off the end there. All right, so we have 2 more questions. This one we're going to go pretty quickly through because we've talked about this so many times. We're going to find the perimeter and area of, remember we're talking about a rectangle. So what I like to do is just draw my rectangle. And a lot of people will say, well, what if that's not exactly 9 4/800 centimeters and exactly 4 4/10 centimeters? It really doesn't matter because we're just drawing it as a picture to help us visualize the problem. So the first thing we got to find is the perimeter. Remember, you add all the sides to find the perimeter. In order to find the perimeter, you have to add all 4 sides. Now keep in mind, if there are 4 sides of a rectangle, you have to add all 4. We know what this side is going to be because it's a rectangle. Opposite sides are congruent. And we know what this side is going to be. In order to find the perimeter, you would add all 4 of those sides. Whatever you get for the perimeter, your answer is going to be in centimeters. For the area, remember to find the area, you take the length times the width. Remember, we looked at it as kind of a giant array. The length times the width. And when we do the length times the width, so that would be 9 48/100 times 4 4/10. Whatever we get as our answer here, remember when we're measuring area, we're measuring how much space is on the inside of the shape. That's going to be in square centimeters. So I'm going to write square centimeters. Now, a lot of people will get caught up and try to divide by 2 there. Remember, we only divide by 2 when it's a right triangle. If this had been split down the middle, because that would be split up into 2 right triangles. So we don't really need to divide by 2 in this case because we do want the area of the whole rectangle. Just remember, perimeter is regular centimeters. Area, we're looking at the inside. We're measuring it in square centimeters, which would be the length times the width. And moving on to the last question. This question is brought to you by Charlie Clem, who wrote this for me last week, and I typed it up into a word problem, so I'll read it for you. One day, Logan was playing Flappy Bird. He was so good at it that he decided to make his own harder game called Jumping Kiwi so that he could have a challenge, and he has said that he's going to try to make that game. Ryan was the first one to download the game and play. He played the game for 32 6/10 minutes. Jackson downloaded the game next and played for 48 minutes. Will played for 104 92/100 minutes. Logan didn't tell them, but he was charging them to play the game. He charged $17 per second. Come on, Logan. Give us a break. How much total did he make from them playing the game? So the first thing I would need to do here is I would need to figure out what is the total amount of time that these guys played the game. So I know that, let's see, Ryan played the game for 32 6/10 minutes. Jackson played for 48 minutes. Will played for 104 92/100 minutes. So we have these 3 times, and that is an exact time, Will. That's impressive. Hopefully the game, I guess it took your stats. So what we're going to do is we're going to add those 3 numbers together. That's going to give us the total number of minutes. So I'm going to go over to the side and do that. So I'm going to take 32 6/10 plus 48. And remember, that's 48 wholes, so I'm going to put 48.0. Jasmine, this would be another example of a time when we are adding and subtracting decimals. And 104 92/100. I like to think that she just asked me that because she wanted to make sure that all of you knew that. So when we add these together, we get 185 52/100. 185 52/100. Now, notice this is 180. I'm going to go to the next page. Go over here. This is 185 52/100 minutes. Because that's minutes, that's not going to help us too much. We need to know how many seconds that would be. So keep in mind that a minute is bigger than a second. It takes 60 seconds to make 1 minute. So what we're going to do is we're going to take this number up here in order to find the number of seconds. We're going to take this number and we're going to multiply it, 185 52/100. We're going to multiply that number by 60 to find the total number, put a decimal there, to find the total number of seconds. Now, once you've found the total number of seconds, we have to keep in mind, this is the total amount they've played, but the question wants to know how much are they going to have to pay. So once we found this answer right here, remember that he charged $17 each second. So we're going to take this number, and whatever we get here, take this question mark, we're going to multiply it by $17 because remember that's how much he charged per second. So our idea here is going to be to figure out, well, how many total minutes did they play all together? How many seconds would that be? That's why we're multiplying by 60. And then if it costs $17 for each second, how much are they going to have to pay in total? All right, so I really appreciate all you guys coming tonight. One last thing I want to bring up before we stop tonight is the challenge problem of the week for this week, which is the people on the bus problem. If you guys haven't read this problem, I'm promoting my own problem, but if you haven't read it, please go back and look at it. This is a great opportunity for a problem where you can A, try to work backwards. Working backwards is a great strategy for this problem. Or B, a lot of you guys have asked me a lot about guessing and checking. When is a good time to guess and check? This is a great problem to guess and check, and it involves fractions. I would be more than happy to work with anyone who wants to try it out at lunch, and I'll try to make some extra copies. I have some copies in the room. Make some extra copies if you want one. Come and ask for one, and we can work on it together even. But give it a try. You guys can do this, and I want to see you challenge yourself a little bit to a problem that might be pretty tough at first, but I think that you guys are definitely capable of doing it. So I challenge all of you guys to go and to try that problem, and I would be more than happy to help in any way that I can. Thank you guys all for coming tonight, and this is our last live session of 2017, so I will see you guys back here next year, and I'll also see you in class tomorrow. All right, bye.